Okay. So, it's been a long week and I think we're all a little bit tired. So I'm gonna try to be have a little bit of lighter discussion, and I won't try to cover a lot of calculations like it's been in the previous talk, but I want to set up the basics. So I'm gonna talk about just quenching and how some of the techniques were have been discussed here apply for this case. So well, just as a disclaimer, anyone who has already studied in detail what is called the VDMPS formalism probably has already seen some version of what I'm going to talk about today. But bear with me, I'm going to try to look at it from different perspectives and show you how the same calculation can be set up in different ways. So just as a brief introduction, normally, when in collider physics, we talk about the experiments where you have, like, for example, PP collisions, where you have like very high energy particles go with towards each other. You have violent collisions, and you have some event in which you see stuff coming out, and you might see several particles. You will see lots of particles coming out of there, but in general, it's the typical event. You see things back to back, right? You see like you have a collision of quarks or collision of gluons, and then you have one very energetic quark going in one direction, and another one going in the opposite direction. And because these things are created here with a very high virtuality, these particles in general radiate some gluons that can even become quark-anti quarks, and in general you have some sort of parton showers in the vacuum, right? So this whatever is created in the high energy collision is going to radiate something, and you create jets in general. Is what you see in QCD collisions. Now, if we move to heavy ion collisions, AA nuclei, normally with the same type of nuclei on both sides. What you have is not just a small proton that is going very fast, it's a big fat nucleus, which, because it's going very fast, will usually look like a compressed in one of the directions. And this has like a bunch of different nucleons inside. I'm sorry, my artistic abilities are not I'm not very good, but still you got the idea. You have this, and now the collision is you have a lot of collisions inside, and what happens is that you create some sort of medium where for some amount of time it looks like you have like the confined partons, and it's what people call the quark gluon plasma. But in the middle of all that, fluid that is created, you also have like very violent conditions like the ones that we're used to in PP. So you can have very high energetic partons that come out from there. And the same stuff that we have here also occurs. You also have some sort of parton shower. These things radiate. But because you're inside a medium, you're going to radiate more. So in general, these particles that come out in different directions, whereas here, if you reconstruct the jets and you measure the total energy going in both directions, usually it is back to back, it's well balanced. In this case, it is not always well balanced. So one of the particles can lose more energy than the other one, either just by the collisions or because of the induced radiation, right? And that phenomenon of the the energy loss due to interactions with the plasma is what in general is called jet quenching. Right? So this is something that was observed from the very early heavy ion collisions that were done on Rick. And the question is, can we quantify that phenomena, and can we set up an analytic calculation where we can figure out how this emission process is modified, right? So in this case, like for the PT collisions, imagine that if you look only at like one of these guys that escapes, like some part is created in the initial collision, it has a high virtuality initially, so before it goes on shell, it has to radiate. And you have vacuum radiation. And that's what we call the vacuum partner shower. And this is something that has been a lot of people have been working on that for a very long time. It's still a very active field of research of how to do good partner shower, but this is not the subject of this of these lectures. In principle, what we would like to know is how those partner showers are modified when you put that inside a medium. So if you have the same thing, so if you look at now one of these guys, one very high energy particle that is created in some, I'm just gonna draw it like a box with some length. I don't know much of the details of this for the moment, it doesn't matter. And now I also have some radiation, but the showers is not going to be the same. Maybe I have some additional wide angle radiation. Maybe it's more likely to have extra gluons in different places, and in general, these particles are going to radiate more than what they will do in the vacuum. So inside a medium, there is additional radiation. Which we call that is additional radiation called medium induced. And of course, the full modification of the shower is way too complicated for what we know so far. It's beyond the scope of current techniques. But so what we can try is to just look at what is the simplest thing that we can do. And the simplest thing that we can do is just imagine that we have that high energy particle that is going through some medium. We will probably assume some very simple picture of that medium. So we imagine that it has like some sort of scattering with some medium constituents. But at some point, it emits this supported, it emits a gluon. So imagine that I have an initial energy of that particle, which is very high, and then I emit some gluon, which I'm going to write the energy omega. And I will try to describe how we can calculate the spectrum for such gluons. Right, this is a calculation that was done more than 20 years ago. Still, we're still working on that, on different variations, on relaxing different approximations. But this is like the basics of most of the theory for jet quenching. So how is this interesting, and how does this connect with the rest of the stuff that we've been doing in this course? So first, of all, we're going to consider that the energy of that particle to be very high, right? Very large. So this is like it's a boosted particle, and in that sense, when we have a large boost for the objects that we're considering, these Light-Cone techniques are always useful. But let me just tell you why this process is interesting in this context, and how it is different from, for example, how it is different from QED. So if you were in the QED case, so imagine you have an electron instead of a quark, and you want to, and again, you're in some sort of QED plasma. I'm sorry, I'm going to be writing the same diagram over and over again. It's going to look a little bit repetitive. And I want to know what happens when I radiate this gluon. If this had an energy, the probability of radiating that gluon, if I consider a spectrum, like this, what happens when the energy goes to infinity? If the energy is very large, this spectrum goes like 1 over the energy of the particle. And that is related with the fact that you can only hit that initial particle. Imagine for a moment that you have a non-shell particle. A non-shell particle is not supposed to radiate. So if you have the medium induced part that comes as a consequence of hitting that particle, is because after each hit, it can become a little bit of shell and radiate, right? But for that, this is like the equivalent of the classical electrodynamics process, in which you said you need some acceleration to radiate. If you have an electric charge and that charge has some acceleration, the consequence is radiation, right? But if your particle it has a very, very high energy, then just you have to hit it really hard to actually deviate it from its trajectory, otherwise the acceleration is going to be very small. So when the energy goes to infinity, this is a particle that is very rigid, and it's hard to make it move so that it will emit something, right? But the problem is that the difference when you go to QCD is that you have an additional diagram, which is this diagram, right? You can emit and then hit the emitted gluon. So this is so you have an initial energy and you're going to emit a gluon with an energy omega, then the probability for that when the energy is large, it was like 1/omega, not like one over the energy. So that also does that we can have that limit is more interesting in QCD. You can have very high energy particles. You can look at that limit where that energy goes to infinity and still have something that doesn't necessarily go to zero when you take that limit of the infinite energy, right? Now, what we need to do is to find a way of taking into account all those multiple scatterings that we will have, and see if we can resum them in some way. And in that sense, the first thing that we can do is just go back to what Tolga was teaching us yesterday on how to use how to write some interactions in a background medium, in a background field. So, okay, so if you remember, so if you remember from Tolga stuff yesterday. He was considering a case where you have some asymptotic state at infinity. Okay, so just a schematic. What we want to do is to see what happens when you have a particle that has a bunch of scatterings, which we are going to model through a background medium. Okay. So, in this formalism, this is something that was also from Guillaume's talk. You have some what was called this potential that depends on X plus, which was written like this. And then these spaces that the community current. Okay. And that is the interaction potential where for simplicity, we're just going to assume that that we're going to a background field. So this is a classical field. Today I'm not going to say what we do with that classical field, but tomorrow I'm going to tell you how we model the correlations in that field. And well, this one has some. This is composed of quantum field. Okay. So now, what Tolga did yesterday was to say, okay, we're going to apply a boost. A boost parameterized by this parameter. I use eta because I already used omega somewhere else. And the idea was that so he did all the details, he worked it out, and well, what he found is that the different components of that current scale differently under this boost. The plus current gets this large boost. Then the per components do not get a boost, are not modified, and the minus component of the current, it's the inverse. So the conclusion was that we only care about this. This is if this is quantity is large, then this one is suppressed, this one is the same, but this one is enhanced, and we only care about this component is the one that is going to give the largest contribution, which at the same time means that if I have something that looks like A mu, J mu, we only care about the A minus A plus, right? And then the other way that that the boost will enter is this potential actually looks after some manipulations. What we have is that we can write this as if you have this factor here for the x minus in the field, and in the plus current, you have that factor there for the x plus. And then what Tolga said was in the strict diagonal limit, you just say this is 0, this is 0. So what that means is that you can take this as the transfer integration. I'm not even going to write the 0, I'm just saying this is independent of x minus now. So my integration over x minus acts only on this one. But now this one has no x plus dependence. And then what Tolga did was just look closely into how this is composed of creation and annihilation operators. But the idea is that at the end you get this is the piece that survives, and it's going to be diagonal in transfer space, right? So let me just summarize what are the kind of approximations that are being done here. But first, we're saying only A minus contributes, not the only component. There's no E pair, but there's no E plus, right? Then I'm saying A minus does not depend on x minus, and J plus does not depend on x plus. Okay. So what we're going to see is that all this has this comes from the equation, but this has different physical consequences. For example, this will imply that there are no spin flips, for example. So, the Dirac algebra would be trivial. and the elicity of the quark will not change. I will elaborate on that a little bit. Now, if this, the fact that I minus doesn't depend on X minus, what tells you is that there is no, the external field does not change the plus component of the quark. So if you imagine that, so I'm writing here everything in terms of coordinate space, but if you were to take a Fourier transform of this, the conjugate of X minus is P plus, and that means that if this is independent of X minus, I will have a delta function of P on the P plus for A minus, which means that these lines, this is where the A minus will show up, and each of this is happening. There is no flux of plus momentum in each of these vertices. It's only transfers. Okay. Okay. Transverse momentum.
What about the minus momentum?
There's no minus momentum. There's no minus momentum conservation. You're doing, if we're going to do this calculation in like a perturbation theory, each of these lines, at each vertex you have conservation of the plus component and the minus component, and the plus component and the per component. So the minus component is always such that each particle is on shell. So there's no such thing as transfer of minus momentum. Okay. And then, what does this mean in this picture? So remember that then, in general, when you have, if you were to have some X plus dependence in the, we can always write this as in terms of or operator evaluated at equal at X plus 0. So remember this, this T operator is, if I have my P minus operator, which has the role of the energy in this formalism, that the idea is that I can decompose this as this T plus V for the sake of defining the interaction picture. So this T and this T acting on a Fock state with a definite P plus and P per has an eigenvalue. My correction here, I think is so close to this. That T acting on some Fock state with some definite P plus and P per. This separation is usually defined in a way that this gives you just then the P plus in the vacuum. So just P per square plus minus P square P plus right. So for the sake of these lectures, I'm going to use only massless particles, so don't forget about the mass. But just remember that the mass will always enter in these kind of things. If you ever want to extend these calculations to a massive quark, you have to go back and put all these m squares everywhere. So when I'm saying that that I'm neglecting that dependence on x plus, what I'm really saying is that that combination of p per square over 2p plus times x plus, where x plus can be anything. So it can be as big as if I imagine that this extends from some position 0 all the way to some L, let me call it L plus to emphasize that is in the plus direction. What I'm saying is that this times some L plus is very small. Or that this I'm taking those phases to 0, right? So taking those phases to 0 is so now the picture that we're going to keep in mind now is instead of just having some boost parameterized by some eta, I'm just going to think about in terms of kind of very large p plus, right? So in general, things that have p plus in the denominators are supposed to be very small because p plus is supposed to be much larger than everything else. When p plus is the plus component of the high energy initial part, right? And so this condition that we can ignore these phases is also when in some context, like what was Tolga explaining yesterday and today, people also see it as like this length being contracted to almost a point, and you see the interaction as if it is just a shower, right? But that particular approximation is not going to be very suitable for our case, because in this case of the jet quenching formalism, you are thinking about a particle that was created either inside the medium or briefly before the medium was created. So you don't really have time to emit very much before you have to interact with the medium. Okay, so this whole picture, when you can ignore these things, is good for let me see. I can erase here. So that picture where you can narrate, when you can neglect the length of the medium, is good for the kind of processes that Tolga was talking about today. For example, if you're thinking about a DIS process in which you have an initial photon, which then splits into a quark anti-quark, and then you have a very localized interaction with the background field. This is the place where you interact with the background field that looks like a very contracted piece of matter. Right, then in that case, you say, okay, this is good because I only need to take into account these multiple interactions with the medium in this very reduced space, and I can imagine that this transverse coordinate, there's some x1 pair that is fixed during the interaction, and the same thing here, the pairs that is fixed during the interaction. You can also think about these things in the context of proton nucleus collisions, where you imagine that one parton coming from the proton has also that kind of interaction. Maybe it emits a gluon before it interacts with the medium, but the medium is just a nucleus that is very localized, and the incoming parton that is already in my incoming proton has had a lot of time to emit this gluon before it actually sees them, before it actually has the scattering. So these two particles are already well separated, and I can imagine that this coordinate is different from this coordinate, and that those coordinates are frozen during the interaction. right? That formalism is suitable for that. In that case, I don't really care how wide this is, or well, that's just an extra parameter, but the approximation where the coordinates are fixed is good enough. But now, if what I'm thinking is that if I want to emit something inside here, then I cannot take this. I cannot take this medium as like completely collapse into a shock. What I want to do now is to have that medium have some finite extent, go from some 0 to some plus, and then at some point here, I emit something. So this was in some coordinate expert. And what happens with the gluon that I emit? If I keep using this formalism in which at the end the interactions are diagonal in expert, and I assume that those transverse coordinates are frozen during the interaction, then what I will end up doing is having the gluon exactly on top of my quark, and a gluon on top of a quark is completely indistinguishable from just the quark, right? So that's not good enough for the case that I want here, which means that for the interactions of this gluon, I need to be able to let that transfer coordinate vary during that time. I want to be able to have a finite length and not collapse that to just a point. So the easiest thing that I can do is relax this approximation. Okay. So what I'm going to do from now on is I will still assume that A minus is the only one that contributes, that A minus does not depend on X minus, but now I cannot completely neglect that X plus dependence, and I will have to use these kind of things, which will allow my particle to move a little bit on the transverse plane, and I will show you how that shows up in the calculations. Okay. Okay, so what I want to do is something like this, is try to see how can I take into account all those interactions. So first of all, what's the vertex that I will be using? If I have some initial momentum here, final momentum here, I've been saying that this is going to enter like an A minus and evaluated some position X. So what I have in the so this will have just a spinner for my final momentum. This one at least. I have a Meijian and there's a gamma. I said there's a gamma plus, an A minus, and it's like X. As plus. Right. and I probably have to integrate overall components of X. So that's this next standard vertex contribution with an external field. And what are the things that we need to look at here? So, first, what I said out, then the spinor algebra, the Dirac algebra, it's trivial. This is U bar of PF, some elasticity, gamma plus, yeah, it's fine. This is equal to the square root of 2 plus the square root of 2 plus times the function of h prime. Okay. So the listing never changed, which means that I'm going to completely forget about it and I will never write it again. And we also, one of these integrals is an x minus integration. The field doesn't depend on x minus, which gives me a delta function in the p plus components, which I had already anticipated, right? Which means that it is power 2 pi delta of plus and now these two things are the same, so I will have a factor of 2 plus and then I have what is left here is the integration over x plus integration over x squared. There's a 90 somewhere. And now it's place that I have here. I have them. There will be an. So okay, so this remember that for these particles, the minus component is always to make it on shell. So minus here looks something like Earth squared divided by 2 plus and minus squared divided by 2 plus minus x plus and then the first part the Earth minus the I. And the field. Okay. Well, that's just the vertex. Now I'm what I really want to do is to see. So I want what I really want to calculate is what happens if I have some final momentum. So I'm going to put here explicitly on the state at some plus position. Now we know that the evolution from one to the other is a path order exponential of this. Of the interaction potential. So, what I want to calculate is something like this, is I want to have, just like putting here some initial potential here, some initial momentum here, and I want to end up with some final momentum here, right? And I'm saying this occurs at some initial xi plus, and here it ends at some final x final plus. And let me call this as final initial. And I want to look at it order by order, see what happens. I should probably go a little bit faster. Slow. Okay, so if I look at it order one, what do I get at order one? It's just this vertex, right? It's just this vertex, except that on the endpoints, I'm going to have some extra phase factors because of the fog states that I put at the end. So this is easy to check, that this is just 2 PF plus times 2 pi delta of PF plus minus PF plus times. And I have now an integration for x plus from x I plus x final plus and of. Now I have this from what I calculated in the vertex, I have these factors here x plus, but now my states in the ends are going to give me similar phase factors, but at the endpoints. So that is again leaving some more space. Approach field and use factor of the times the other factor, which is minus I. The I per square I plus x plus minus x I plus. Okay. So that's what it looks like. And now now what I'm doing here is just trying to keep track of those phase factors that appear everywhere. Okay, please, if there's any questions or any given time, just interrupt me. So those are in the completely icon approximation that Tolga was explaining. Those these phases are 0, which means that these factors is just 1. And it leaves you with only the only the field A minus, right? Which is just the first term in the path order exponential that appears, the Wilson line that appears in that case. Now, these factors, let me just, I'm just gonna give them a name because they're gonna show up all the time. And so these factors is what we call, this is just a two-dimensional free propagator. So I'm gonna write it like, this is G, I'm gonna go G0. So I'm gonna make sure that I don't screw up the notation. So for example, if I look at this one here, I'm gonna write it as going from X plus to Xi plus, and if there's also associated a momentum variable, here is Pi curve, and some energy out, some Light-Cone energy, some plus components are. And I would just say, okay, the definition of this is just that space. Okay, and then I can take the Fourier transform of this and say, okay. Let me just change the notation here just to make it more. Let me call this okay, X2, X1, and just remove these indices. Curve of, X1. Plus, I'm just going to call this with a base factor of minus I third into X2 third minus X1 third. I'm just, this is the notation. I'm going to be using notation in the sense that Fourier transforms of the same object. I'm gonna use the same object. Just look at where it is evaluated, and so this is something that I'm going to be doing in this calculation over and over again, just doing only transverse Fourier transforms. The longitudinal components, I'm not going to touch them. I always have the P plus and the X plus will always be explicit, but between X perp and P perp, I'm going to be switching back and forth. Okay. Now, because we know this. This is a very simple. This is a Gaussian. This is a Gaussian integration. So I mean, we can write explicitly this formula. I'm really not going to use it, but I'll write it just for convenience. And also this object also has a path integral representation, because this is the again, this is just this is a free propagator in two dimensions where the P plus plays the role of a mass, and this can be written as the path integral R, where the endpoints are R at x1 plus is equal to x1 R at x2 plus x2 third. And this is the exponential of I plus over 2 of the integration from x1 plus x2 plus psi of R dot of psi square. Okay. For the moment, this is just a formal way of writing the same thing. Is that I have some nice properties that we're going to use later. Right. For example, that propagator, if I have the if I integrate over x to the third, and I have the x3, x to the first, x x2 plus third plus. It's important to always do this is the right thing. X2 plus. This is this provided that x1 plus is less than x2 plus less than x3 plus. We also have to keep in mind that in these cases, the plus components are always ordered, right? So this is just a convolution property for this propagator. It will be useful later. But this is the kind of things that are easy to write, for example, in this language, while if you use the complete expression, you have to do some Gaussian integration. Okay. Anyway, so okay, I'm going to write this. So this means that this first order that I was writing, the delta function, and then I'm writing this. This is just, what I'm writing right now is just notation. And it's just saying I have x plus integration, and I want this be 0 from x final to x plus yes, there yes plus. Then I have so that here I have transfers integral. So I'm going to keep a using notation, and I'm just going to write that as an a minus at x plus, but in momentum space, we have per minus the per, that's the transfer, the momentum transfer, times the vacuum propagator. Okay. Very simple. Vacuum propagator, interaction, vacuum propagator. That's it. What I'm doing here is to make it explicit that the transverse part is different from the longitudinal part. Okay. Now you can write the same thing in coordinate space. So, if you write it in coordinate space, where you have is still the same. But here some space because there's some transverse integrals, so fix that later. And that means that we have an x plus, now we have some x curve that goes to x plus x squared plus, then I have the interaction x plus x squared, and then a propagator that goes from x to xi yeah, plus. And I have to integrate over both x squared and xi squared, and I have to put the Fourier transform of that also, which goes like into the I df squared divided into x squared minus I di squared. Okay, and it's easy to check that you can go straight from one to the other just by taking the Fourier transforms of all the things. Okay, so that's just the initial term, and now we're gonna go a little bit faster. What happens with the second order term?
You have a brief application there.
Yes. So now, if I'm looking at them at this term, now I have a PI. We call this P1 in the middle. Yeah. The only difference with this diagram is that now there's an intermediate propagator here, right? And that intermediate propagator so in Light-Cone, if we do this in the Light-Cone perturbation theory that we have been doing, normally for intermediate states, we have the energy denominators, but we don't have the energy denominators in this case for the simple reason that we are not performing the X plus integrations. I'm always leaving the X plus. The X plus is explicit. If I were to perform the X plus integration, I will have, so I have an X plus here, and I have an X plus here. And that integral will bring down precisely the denominator with the difference of the P minuses, right? So that's where the energy denominators come from. And since I'm not doing the X plus integrations, I don't have energy denominator, which means that that intermediate particle only gives me a factor of 1 over twice P1 plus, right? And that's if you're more familiar with the
In the coordinate transformation of second line, is there an integral of the compass coordinate as a position of A minus?
yes. Forgot it again. Sorry. Okay. So if you're more familiar with regular Feynman diagrams, that's exactly what you get when you integrate. So like normally in a Feynman diagram, remember that we're only looking at it's like because we already computed the spin part, we already got rid of the spinners. We only care about the propagators as if they were scalars. So for example, that in that case, I will have a propagator that goes like 1 over P1 squared plus I epsilon, right? But what we do in these cases is that we always perform them minus integration, right? The P1 minus that goes like with a P1 I P1 minus. And in this case, if I have to, this point is x2 and this point is x1, then I will have an x2 plus minus x1 plus. And you can perform that integration closing the point. You can do a counter integration to pick only one of the poles. And just pick this combination. And what that gives you is that this denominator goes like twice P plus P minus minus P squared plus I epsilon, and the pole in the P minus is precisely what you want. So you factor out the P plus, and this gives you exactly the 1 over 2 P plus. Actually, I should put a beta function here. So yeah, this is just a reminder that normal propagators from usual Feynman rules, when you get rid of the P minus components, they just give you this extra factor, the time ordering, and these are the pieces that we know that come from extracting the X plus dependence from the vertices. So yeah, just a quick reminder. So in any case, I was already keeping track of all these factors. So my new propagator will only give me this additional factor, but that's going to cancel out actually, because now the NCBJ to order 2. How will it? Let me just explain quickly. Remember that the single vertex. When I did the Dirac algebra at the vertex, will give me a square root of this, and the square root of this, and the square root of this. So this one appears twice because it appears from this vertex and appears from this vertex. So I get a power of P1 plus, which will cancel exactly this guy here. So it disappears, and I end up staying with the. I keep that so that this factor that I have here was precisely from the rest of the factors of the vertex. The delta functions still, I will have a delta function for P plus in each of the vertex. So I have an overall delta function. So this whole factor is still there. And now I have two integrations. Actually, what I will get is exactly something like this. So I'm going to write this version first, the transverse momentum version, which is I have a dx2 plus, which goes from xi plus to xz plus. Then I have a dx1 plus that goes from xi plus, but this one can only go to x2 plus. They have to be ordered, right? And now I have 2 here plus and IG and field X2 plus minus 1 per times now I have a linear propagator that goes from X2 to X1 1 per that the F plus, well, it should be P1 plus, but all the P pluses are the same. IG A minus X1 plus at P1 per minus the I per times my last propagator and plus and again I forgot that there are the X1 per and the X2 per. Okay, so it has the same structure, just I keep doing the same propagator, field, propagator. I can do the same story for this for the coordinate space one. It's going to be the same. I still have the Fourier transform at the edges, but I will have an extra intermediate step. Okay, and now remember that in the case where we had the strict Eichmann limit, this G in momentum space goes to 1. If it goes to 1 in momentum space, that means that in coordinate space it becomes a delta function, which means that what we already know, that all the A's are going to be in the same transverse coordinate. Okay. And you can keep doing that in general and do that to order n.
Really not the integration of the classes to either to on the side.
Sorry?
But we're really not doing the X classes.
It's because I keep it always in my in the fields. So I mean
The field can be time dependent.
yes, but I don't know how. I want to keep that time dependence generic. So we can write them the n term. What is the n term? Just the an integral from x I plus n plus x n minus 1 plus x n plus x I plus then I have integration over all the dx of 1 curve all the way to dx and curve, and then I have all these propagators. Is x plus x n plus curve plus times IG A n plus third minus n third. Let me write another one. And then no, sorry, I made a mistake. There's no n. N minus 1. N minus 1 third. N minus 1 third minus n minus 2 third. And dot. And at the very end, I have an I a minus or it at 6 1 plus, or I have a P1 third minus P I. Okay, and that's my end time, right? I have a bunch of. I can write this as a product because yeah, I'm a little bit lazy to work it out.
Why are we integrating in the transfers coordinate? There.
It was all the intermediate transfer coordinates are always integrated.
You have the integrals.
That's when you do the 2 transform that you need to do the integration, right?
No.
So therefore, when it doesn't have Penrose position.
Yeah, that's true.
Like this, I have to integrate over these positions.
Yes, but
In the actual integrants, you don't have any XT dependency.
When it's in.
In the oh yes, you're right. I'm
You
sorry.
only include it when
You're right. I already did I did the first transform and put it here. Yeah, you're completely right. I'm sorry.
X two the same thing.
Yes. I forgot to put it a couple of times and now I'm putting it where I shouldn't put it. Yes. So that is the end term. So now, okay, we want to add up all these things. Okay. And so what do we do to sum the whole thing? So okay, so again, if you forget about these 3 propagators, what you have is just is just the order product of the A's, the limits and the integration, make sure that that's order. So I can write that. So I can write that as 1 or n factorial times the order product from xi to xf, and the sum just exponent is just a part order exponential. Okay, no need to get into the details of that, and that's the usual Wilson line. Now, if I have all these intermediate propagators, there are several things that I can do. So, one thing that you can do, that is what is usually how people explain these things, is to say, okay, my propagators are path integrals. Okay. So if I say that, let's just do the DS1. Remember what DS1 was? DS1. Okay, I always have this initial factor. So if I want to do DS1, I had it there, my erasing. Let me do the one in coordinate space. So I had the X 1 plus 1.5 plus if I'm doing coordinate space, that means that I have to integrate over a bunch of transverse coordinates, which includes the initial one, the initial and final ones. This one I'm going to stay there with the phase factor. This is going to stay there, but I won't worry about this piece. Then I have I also have an integration over X1 curve. And what I had was I had a propagator from X1 plus X sorry X plus X third X1 plus X1 third. Let me just not write the P plus all the time. A minus calculated by X1 plus X1 third. X1 plus X1 third. And then each of these it's I write like the path order the path of the path integral of this integral from X1 plus X plus dot square, and this one is the same. This one is the integration. I should probably write the R divided at X1 plus is X1 third. R divided at XF plus XF third. And this one is the exact same thing, but with different limits. And when you write it like that, then you realize that this path integral, this is going from X, this is from X1 to XF, this is from XI to X1. You can combine them into only one of them. This transverse integral, what it's telling me is that I'm integrating over the position of my path in the intermediate position, right? So and then I take also this integral, I can bring it inside, and this whole thing is just 2 plus times 25. And if I do that, then this is just a path integration where I have R over the next side, XI curve, R over the next plus is equal to X curve, and I have the exponential of I plus divided by 2, and now this goes from XI plus to XF plus I R dot square, and now I have here my G times the integral from
IEP plus.
the plus smaller plus minus x1 plus. Now the x1 part is really r evaluated at x1 plus. Clear what I did? So what I did is I combined the two path integrals, but at the cost of putting this piece here that depends on that now this depends on the path. This is not just before it was a variable that I was integrating over. Now I'm evaluating over a specific path. Okay. And this trick that I did for the S1, I can do exactly the same thing for the SN. I'm sorry, this is not completely correct. I'm missing this. I still have to do a Fourier transform of the endpoints. Okay. Just don't have the space to put it. Sorry. Sorry for being so disorganized. Okay, so I can do that. This is the S1, but the exact same trick I can do it for the SN, right? I can go to coordinate space. I can each of the intermediate propagators write it as a path integral. Paste together all those exponents from the path integrals. And just the fields will be evaluated along the path. And if I do that, that means that that all these intermediate propagators that I have here in between are collected somewhere, and I'm back to having that product of that order product of fields. So let me I'm going to erase this last line and I'm going to replace it to what it looks like. What? R? It's my integration variable. It's a path integral.
First coordinates when you follow your path.
Okay, this is aviation. It's just it's a dummy variable there. So okay, so now I should write that Fourier transform before I forget again. And then I have the path integral where here I'm going to write like this. This is a path order product of okay. which means that I can sum over n now. And if I sum over n, well, now the whole S is that to be not I forgot to write. Forget to put that. I wrote the integration, but I didn't write the phase factor. Yeah. Okay, so this is here that that path integral is what usually people call that's the scalar propagator in coordinate space. Okay. I was hoping to do much more today, but so then having that propagator in that compact form is I mean, it's nice to have like a formal expression, but it's true that it's very little that we can do with the path integrals. So what I'm going to do tomorrow first, I hope to go much faster than this, is to show you properties of this propagator that actually make it more tractable. Okay, and then the idea is to use this to just show what I was talking at the beginning of just how do you use this to calculate an emission. Now that you included that.
Oh, you're blocking the camera.
I was saying that just to not block you from everyone.
Yes, and they wasn't able to see that.
Yes. I'm sorry. Okay, so we'll continue tomorrow. Okay. Any questions?
Okay, I'll see, maybe some from the people online. Don't see any, so thank you very much.